When we think about making AI smarter, we usually picture building one single giant superbrain, right? But what if that's not the answer at all? What if the real key is assembling a team of specialized AI experts? Yeah, we're talking about a new approach that literally creates a collaborative dream team of AIs to solve really complex problems. And get this, they do it more accurately and efficiently than ever before. So let's break down how this AI dream team actually gets built and why it's already outsmarting some of the most powerful models out there.
All right, so here's what we're going to cover. First, we'll get into the big problem with today's AIs, why they're so single-minded. Then we'll jump into how you actually build this AI dream team. And maybe most importantly, how you pick the right captain for the job. After that, we'll uncover the secret to how these AIs actually know their own strengths, which is wild. Then we'll check out the team's report card. The results are pretty impressive. And finally, we'll see why this whole approach isn't just about being smarter, it's also about being way more efficient. Okay, so let's get right to it. Here's the core issue. Even the most powerful AI models we have today, they have blind spots. It's just baked into how they're trained. And the old solution, just throwing a bunch of identical AI copies at a problem, that just doesn't work. It's like putting a team of clones in a room together. All you're going to get is an echo chamber, not real, creative problem solving. And this really shows what I'm talking about, the old way of doing things. On one side, you've got a single model just thinking step by step, all by itself. On the other side, you've got a team of clones trying to have a debate. But here's the kicker. If they all think the exact same way, you're never going to get any new ideas, right? It's this exact limitation that sets the stage for a totally new way of thinking. And that brings us to the solution, a really cool framework called Team of Thoughts. The name says it all. Instead of one AI or a team of clones, the big idea here is to build a dream team of different specialized AIs. Each one has its own unique skills, and they all work together to tackle one problem. So here's the basic rundown of how it works. Think of it like a real-world project. You've got a central manager, they call it the orchestrator, and it's basically the project lead. It gets a problem, figures out a game plan, and then brings in the right specialists from the team to do their part. Then it pulls all their contributions together to create the final answer. So let's dig a little deeper into that manager role, the orchestrator. This thing is really the brains of the whole operation. It's not just a glorified messenger passing notes back and forth. No, it's actively analyzing the task, figuring out exactly which specialists are needed, and then weaving all their different inputs into one solid, high-quality solution. And who's on this team that the orchestrator is managing? Well, they're called tool agents, and you can just think of them as the team's specialists. So you might have one that's a total math whiz, another that's a coding genius, and maybe a third that's amazing at creative thinking. The key is, each one is a totally different AI model with its own unique training and expertise. And this right here is the crucial part, this idea of heterogeneous models. Honestly, this is the secret ingredient. The real power of this team doesn't come from just telling one AI, hey, pretend to be a coder now. No way. It comes from using fundamentally different AI models that have genuinely different strengths and weaknesses. That's where the magic, the real innovation, happens. Okay, so you've got your team of specialists. Awesome. But every great team needs a great captain, right? So how do you pick the best AI to be the leader? And once you have that leader, how does it know who on the team is right for each task? This brings us to the system's two-part secret sauce. First, picking the right leader. And second, making sure that leader has a team that, get this, actually knows its own strengths. Let's actually start with that second part of the secret sauce, because it's a huge deal. Any great manager needs to know what their team is good at, right? Well, this system introduces a pretty radical idea. What if the AI agents could accurately assess their own skills and then report back to their manager? And this diagram really shows us how that works. Check it out. When a task comes in, the orchestrator doesn't just guess who to give it to. No, it actually consults these tool agent self-assessments, which are basically resumes written by the AIs themselves. It's wild. So based on those profiles, it picks the right agents for the job, and only then does it move forward. This whole idea of informed delegation is absolutely key to why the system is so successful. So the whole setup really boils down to this simple but super powerful two-step process. First, you calibrate the orchestrator. You basically test a bunch of different AIs to find the absolute best one for the manager job. Then second, you have each of the tool agents profile themselves. Each specialist agent literally writes its own resume by analyzing its own performance on different kinds of tasks.
Okay, so this all sounds amazing in theory, right? A self-aware AI dream team. But the big question is, does it actually work? Well, now we get to the payoff. Let's look at the hard data. Because the research shows this team of thoughts idea isn't just a fun concept, it is a massive breakthrough in performance. Just take a look at this table. It compares team of thoughts to another system called Agentverse, which uses a team of clones, so no diversity. And the difference is staggering. On a tough math benchmark, the accuracy jumps from 80% all the way up to over 96% with the dream team. And you see a similar huge leap on the coding test. It's so clear. That diversity of specialists really, really pays off. And this bar chart makes it even clearer. Here we're comparing the team against a single, very powerful model working alone. On its own, that model does pretty well. It gets about an 87% score. Respectable. But when you put it in the team of thought system as the captain, that performance leaps a full 10 percentage points. In the world of AI, that is a massive, massive gain. Yeah, let's just let that number sink in for a second. 96.67% on a really competitive math benchmark. Look, this isn't just a small step up. This is a state-of-the-art result. It basically proves that a well-managed team of specialists can solve problems way more effectively than even a single genius AI working by itself. But wait, there's more. And this might actually be the most important part of the whole thing. The system isn't just more accurate, it's also way, way more efficient. It's getting these incredible results without just burning through a ton of computational power, which for any real-world use is a huge deal. So the bottom line is this. You're getting top-tier, state-of-the-art results, but at a fraction of the cost. The paper actually says it can be an order of magnitude cheaper than other methods, where you have every agent trying to solve the entire problem. That's just incredible. So how does it pull this off? Well, it's two main things. First, something called agent parallelism. Since all of the specialists are independent, they can work on their piece of the puzzle at the same time, no waiting around. And second, it's got strategic token allocation. The orchestrator is smart about its budget. It only calls up the agents it actually needs, and it can even ask for short, to-the-point answers, which saves a ton of computational resources. So when you put it all together, what this really points to is a pretty fundamental shift in how we should be thinking about advanced AI. Maybe the goal isn't to build that one, single, all-knowing superbrain. Maybe the future is actually building a collaborative society of specialized AI agents. And that leaves us with a pretty big and fascinating question. If we have this AI dream team ready to go, what's the first huge world challenge we should ask them to tackle?
All right, let's jump right in. Today, we're talking about a new kind of AI. It doesn't just make virtual people. It makes virtual people that feel like they're actually present with you, in the same room. The whole system is called Sarah. And honestly, it's a huge step toward a much more believable digital future.
But first, let me ask you something. Have you ever been in a VR chat or played a game and just felt that something about the characters was, I don't know, a little bit weird? They're talking, they're moving, but there's this weird glassy-eyed disconnect. If you've felt that, you're definitely not alone.
In this picture, this gets right to the heart of that weird feeling. You see, most current AI agents, they're programmed to react to your words. But as you can see here, if you move around, they just kind of stare into the middle distance. It completely shatters the illusion. It's like they have no idea you even exist in the same space as them.
And yeah, there's actually a name for this whole thing. The uncanny avatar problem. The thing that's missing, the secret sauce, is what's called spatial awareness. It's that basic ability to know you're there, to track your movement, and to react, like a real person would.
Okay, so that's the problem. What's the solution? Well, it's this huge breakthrough at the core of this research, a whole new kind of AI that is, you guessed it, spatially aware.
And this diagram, it really lays out the whole idea perfectly. The goal is no longer just making an avatar that can talk at you. The real goal here is to take in all this information about you, where you are in the room, what you're saying, and use it to generate a 3D avatar that responds to everything. It's not a one-way street anymore. It's a real, dynamic conversation.
And the system that pulls all this off is called SARA. It stands for Spatially Aware Real-Time Agentic Humans. It's a bit of a mouthful, I know, but trust me, every single one of those words is important, as you're about to see.
So what's the big deal with Sarah? Well, it's the very first system that manages to juggle 4 massive things all at the same time. 1, its gestures actually match what it's saying. 2, it's spatially aware. It follows you with its head and body. 3, you can actually control its gaze, which is huge. And the real kicker? It does all of this in real time, fast enough to run smoothly inside a VR headset.
All right, let's pop the hood and see what makes this thing tick, shall we? Don't worry, we won't get too bogged down in the super technical stuff.
So from a bird's eye view, the whole system works like a pipeline. On one end, you've got stuff coming in, your location, your voice, the agent's own voice. All that data gets fed into this smart generative model, and on the other end, it spits out this super fluid, responsive 3D motion for the avatar.
Now that engine, that generative model, really has two main parts. First, there's something called a causal VAE. You can just think of it like a super smart zip file for human motion. It takes all that complex motion and compresses it down into just the essential bits. Then you have the flow matching model, which is kind of like the artist. It takes that compressed data, adds in your live position and audio, and paints a brand new, totally appropriate motion from scratch.
And check this out. This is one of the really clever tricks they used. Instead of representing the avatar's skeleton with old-school joint angles, which can get a little clunky, Sarah treats each joint like a 3D shape, an icosahedron to be exact. It sounds complicated, but what it really means is the whole system is way more stable and has much more precise control. It's a little change that has a massive impact on the final quality.
Okay, let's switch gears and talk about something that's maybe one of the most powerful parts of any human interaction, right? Eye contact.
So the paper points out something that honestly we all just know. How much eye contact feels right is totally different for everyone. It depends on your personality, your culture, the situation you're in. If you try to make a one-size-fits-all rule for eye contact, it just feels, well, creepy. So for an AI to feel real, its gaze has to be adjustable.
So how in the world do you teach an AI to handle something so subtle? Well, you go to the source. You study how actual people do it. On the left, you're seeing a real human conversation from the data they trained the AI on. And on the right, that's the geometric model Sarah uses to basically understand and copy that behavior. It just looks at the direction the agent is facing versus the direction to the user. And all that math spits out this really neat metric they call a gaze score. It's just a number from -1 to 1. 1 means they're looking right at you, -1 means they're looking completely away. But here's the brilliant part. You can actually tune that score in real time to get the exact level of eye contact that feels comfortable for you.
Okay, so we've got motion that's aware of you, we've got a gaze you can control, but the last piece of this puzzle, honestly, it might be the most mind-blowing part, the speed. Making it all happen instantly.
See, here's the problem with a lot of the older models. They had this one huge flaw for live stuff. They were non-causal. That basically means they had to peek a few frames into the future to figure out what to do now, which is fine for making a movie, maybe, but in a live chat, it creates this awkward, impossible lack.
But Sarah, it's completely causal. And that is a game changer. It means the AI doesn't need to see the future. It just reacts to what has happened and what is happening right this second. And that allows it to respond to you instantly, with no delay you can possibly perceive.
And when I say instantly, how fast are we talking? We're talking over 300 frames per second. I mean, to put that in perspective, your fancy VR headset is probably aiming for 90, maybe 120 FPS to feel smooth and avoid motion sickness. 300 is just incredibly, incredibly fast. And this table here just makes it crystal clear. Look at the old methods, the baselines. Not only are they 3 times slower, but remember that non-causal problem? Yep, they're basically unusable for live interaction. Sarah isn't just a little better, it's playing a whole different ballgame.
So let's bring it all back home. Why should you care about any of this? Well, this is the kind of tech that leads to virtual meetings where you actually feel like you're in the room with people. It's what will make digital assistants feel less like a robot and more like a helpful partner. Really, what we're looking at is a brand new chapter in how we interact with computers, one that feels a lot more, well, human.
And that kind of leaves us with one last big question to chew on. For so long, we've had to learn their language, right? Clicks, taps, commands. But what happens when our digital selves, our AIs, become this lifelike, this aware? When they start to become this, well, this human, how does that change everything? It's a pretty wild thing to think about.
Welcome to The Explainer. So today, we're diving into a really fascinating shift happening in technology. See, powerful AI is starting to break out of the cloud, out of those giant data centers, and it's moving into the physical world all around us. We call this Edge AI, and it's all about running that intelligence right on the device itself. I mean, just stop and think about that for a second. What if a simple webcam or the camera on a little robot didn't just capture images but could actually look at a scene and reason about what's going on? This just opens up a whole universe of possibilities for devices that are genuinely smart.
And what's really wild is that this isn't happening on some massive server farm miles away. It's happening right here on a piece of hardware that can literally fit in the palm of your hand. Which, of course, brings us to the big question for this whole explainer. To really get our heads around that, we're going to break this amazing tech down into 3 key parts. Think of it like this. You've got the brain, the body that it lives in, and then the process that brings it all to life. Okay, so let's start with the brain. What exactly is the AI that's making all of this possible? What are we really talking about here? Well, we're talking about something called a vision language model, or VLM for short. And this is a huge leap forward. See, older AI might just categorize things. A VLM, on the other hand, it blends what it sees with an understanding of language, so it can actually interpret the context of a scene and even talk to you about it in plain English. And this slide really nails the difference. A traditional model looks at a picture and spits out a label, like cat. But a VLM can look at that exact same scene and say something like, there's a fluffy orange cat napping on a red pillow. It's the difference between simple recognition and actual comprehension. It's a game changer.
Now, the specific VLM we're focusing on is NVIDIA's Cosmos Reason 2B. This thing was built from the ground up to be super efficient and have really sharp reasoning skills, which, as you can probably guess, makes it the perfect candidate for running on smaller devices, which leads us right into our next section. All right, so let's move on to the body. We've got this incredible AI brain, but what kind of hardware does it run on? It needs something specialized, something small but also powerful enough to handle it. And that's where the NVIDIA Jetson family comes in. The best way to think about these is as a lineup of mini supercomputers. They are purpose-built to take AI out of the data center and put it right into the real world, inside things like drones, robots, and smart cameras. And as you can see, one size definitely does not fit all. You've got this whole range. At the very top, you have the AGX Thor for some really heavy-duty AI research. Then you've got the AGX Orin, which is great for professional prototyping. And then there's the one that's perfect for what we're talking about, the Orin Super Nano. It's compact, but still incredibly capable for these kinds of edge AI jobs.
Okay, so we have the brain, that's our Cosmos model, and we have the body, that's the Jetson computer. So how do you actually put the two together? Let's take a look at the high-level process for bringing this AI to life.
Now, the full technical tutorial gets into all the details, but it really boils down to these 4 main steps. First, you just download the AI model. Then you set up this special software environment called a Docker container. Think of it as a neat little box with everything the AI needs to run. After that, you start up a server to, well, serve the model. And finally, you connect a simple web interface so you can actually talk to it with a webcam. But, of course, it's never quite that simple, right? This quote from the source material really gets to the heart of the challenge here. Trying to run such a powerful AI on a device with very limited memory, well, it's a tight squeeze. You have to be pretty clever about it. And this is how engineers do it. They use these very specific commands, or flags, to manage the device's resources. Think of it like carefully packing a small suitcase for a really long trip. For example, one flag tells the AI to only use about 65% of the memory, just to leave some breathing room for the operating system. Another one limits the AI's short-term memory, so it doesn't get overwhelmed. Each one of these is a careful trade-off between performance and the limited resources you have to work with. Okay, so we've looked at the brain, the body, and the process. Now that we kind of get how it all fits together, let's just zoom out and think about what this all really means for the future. So why does all this matter? Well, it means that developers can now build and test real-world AI applications so much faster than ever before. We're talking about things that used to feel like science fiction, like a search and rescue drone that can just describe what it's seeing in plain English, or a smart checkout that actually understands what's in your cart without having to scan a single barcode. And what's really amazing is that all of this is powered by an incredibly sophisticated AI model that's been shrunk down to just about 5 gigabytes. I mean, that's small enough to fit on a cheap thumb drive, but it's powerful enough to reason about the world around it. So you see, at the end of the day, this isn't just about one cool model or one tiny computer. It represents a fundamental shift into a new era of AI that's accessible and physical. And that really leaves us with a pretty exciting question to think about. When the everyday objects all around us can finally see and reason, what are we gonna create? Okay, so let's just jump right in. We've all seen those incredible, mind-blowing videos the AI can just create out of nothing. But today, we're gonna look past the pretty pictures and ask a much, much deeper question. Can these AIs actually reason about the worlds they're building? Because, that's the next great frontier. I mean, the progress has been absolutely breathtaking, right? You have models like OpenAI's Sora or Google's Veo, and they can take a simple line of text and just spin it into these photorealistic, high-def videos. They're literally creating worlds that look and feel completely real. It's a massive leap forward. But, and this is the big but, here's the beautiful blind spot. While these models are masters of making things look good, they often have zero fundamental understanding of the scenes they create. They don't really get basic physics or causality or even simple logic. It's like, yeah, they can show a ball bouncing, but they don't know why it bounces. So, how in the world do you teach an AI to actually think? Well, a huge team of researchers decided to go back to the drawing board, and they looked at how we humans do it, our own cognitive architecture. They broke down this really fuzzy idea of reasoning into a set of core teachable skills. And this is what they came up with. 5 pillars, the building blocks for intelligence. It's not just one giant skill, right? It's a bunch of different faculties all working together. For today, we're going to zero in on 2 that are super interesting when it comes to video. Let's start with transformation. First up, transformation. The easiest way to think about this is as the AI's imagination. It's the ability to mentally rotate things, move them around, and kind of play with objects in its mind's eye to figure out what's going to happen next. It's not just about seeing what's there, but imagining what could be there. So take this puzzle, for example. To solve this, an AI can't just guess. It has to look at these 4 L-shaped pieces and actually simulate, in its head, rotating each one until they click together perfectly to make a square. It's a pure test of that internal modeling ability. Okay, next up is spatiality. This is all about an AI's intuitive grasp of space. Think about how you just know the layout of a room or how to get from point A to point B without walking into a wall. That's spatiality. It's that fundamental understanding of places and paths. And a maze like this one, it's the perfect test for it. The AI gets a start point and an end point. Its job is to figure out the most efficient way through, understanding that those dark walls are solid obstacles. This is just pure spatial problem solving. So here's the thing. To teach these skills, you can't just show the AI a few examples. It needs a place to practice. A lot. So researchers built exactly that. They built a massive, custom-designed dataset that's basically a giant cognitive gym for AI. And when I say giant, how big are we talking? Well, it's about 1,000 times larger than all the other major video reasoning datasets put together. We're talking more than 1 million video clips, all designed specifically to teach and test these cognitive skills. The scale here is just completely unprecedented. This visual really just drives it home, doesn't it? That huge circle in the middle, that's the new data set. And all those tiny little dots around the outside, yeah, that's the 9 other major data sets in this field combined. It's a whole different league. Okay, so you've built the world's biggest AI gym. The big question is, does the workout actually work? So the researchers took a really powerful open source model and put it through its paces on the new dataset. And, well, the results were pretty staggering. Just look at this jump. The base model started with a score of about 0.37. After being fine-tuned on this new dataset, its score rockets up to almost 0.7. That's a relative improvement of over 84%. The training didn't just help a little. It fundamentally transformed the model's ability to reason. And this is where it gets even more interesting. The model trained on this new dataset didn't just get better, it actually blew past leading proprietary models like Sora 2 on this specific benchmark, especially in areas like spatiality. But, and this is important, look at the human score at the bottom. There is still a big gap. It just shows how hard this problem really is. So what does this improved reasoning actually look like? Well, check this out. In the top left image, Sora 2 is asked to remove the symbol with the red border. It gets it. But notice how it also messes with the other symbols. But on the right, the model trained on the new dataset does exactly what it was told. It removes only the target symbol and leaves everything else untouched. That precision is the whole ballgame. And this quote from the paper just sums it all up perfectly. If a model can't reliably control the scene and follow your instructions to the letter, you can't really prove its reasoning. It might just be getting lucky, making a pretty picture that happens to look right. This controllability, that's the foundation for everything.
So why does any of this matter? I mean, who cares if an AI can solve some abstract puzzles? Well, because this is about getting AI to move beyond just spitting out pixels to actually understanding what those pixels mean.
See, this research is what lays the groundwork for an AI that can be genuinely helpful. An AI that gets cause and effect, that can follow complex, multi-step directions, and that might one day be able to safely and reliably interact with the physical world. This is how we get from cool creative tools to truly capable partners.
And that brings us to the final thought I want to leave you with. For years, AI has been learning from our world, crunching all our text and all our images. But now, it's starting to develop a foundational, almost intuitive kind of reasoning about our world. So the question isn't if it will understand, but what happens when it really truly does.